Every chat app, every multiplayer game, every live dashboard you've ever used is solving the same core problem. How do you let a server talk to a bunch of clients at once, in real time, without anyone waiting in line? Think about a group chat. You type a message, and it shows up on everyone else's screen almost instantly. Under the hood, that's a server juggling dozens of open connections at the same time, forwarding bytes the moment they arrive. Multiplayer game servers face the exact same shape. Every player's move has to reach every other player fast. Live dashboards do it too, pushing fresh data to every connected viewer the instant something changes. Today we're building the piece that makes all of that possible. We're going to build a real chat server in plain C, using raw TCP sockets. No frameworks, no libraries hiding the details. By the end, you'll understand exactly how a server accepts connections, listens to many clients at once, and broadcasts messages between them. Every TCP server, in any language, boils down to 4 steps: create a socket, bind it to an address, listen for connections, then accept them one by one. Let's build that step by step. First, we create a socket with the socket function. We ask for the Internet address family, a stream socket for TCP, and protocol 0, which just means let the OS pick TCP automatically. One quick practical tip: before binding, we set the SO_REUSEADDR option on our socket. Without it, restarting your server right after stopping it often fails with address already in use, because the OS is still holding on to that port for a few seconds. Next we fill in a socket_in structure with the port we want to listen on and an addr_any, which means accept connections on any network interface. Then we call bind, which attaches our socket to that address and port. Listen turns the socket into one that can queue incoming connections, and accept blocks until a client shows up, handing us back a brand new socket just for that one client. That's the entire setup for a working TCP server. Now here's the catch. If we just call accept once, then read and send in a loop, our server can talk to exactly one client. The moment a second person tries to connect, they sit there waiting, because our server is stuck listening to the first client. Picture 2 people opening the chat client at the same time. The first one connects fine. The second one's terminal just hangs, because our read call for client 1 is blocking, and we never even get back around to call accept again. What we actually need is a way to watch the listening socket and every connected client socket at the same time, and react the instant any one of them has data ready, without getting stuck waiting on any single one. That's exactly what select does. It lets you hand the kernel a set of file descriptors and ask it to tell you the moment any of them has something ready to read. Instead of blocking on one socket, we block on all of them at once. We start by declaring an fd_set, clearing it with fd_0, and adding our listening socket with fd_set. We also track the highest file descriptor number we're watching, because select needs that to know how far to scan. To keep this simple, we track clients in a fixed size array, capped at some maximum number of connections. That's fine for a learning project, but it means a busy server needs a smarter data structure, like a dynamically growing list, in real production code. On every pass through our loop, we rebuild that set from scratch, adding the listening socket plus every currently connected client. Then we call select, passing in the set and the max file descriptor, and it blocks until something's actually ready. When select returns, we check each descriptor with fd_set to see if it's the one that's ready. If it's our listening socket, that means a new client is waiting, so we call accept and add their new socket to our client list. If it's one of our existing clients instead, that means they've sent us data, so we call read on their socket. This is the whole trick: one loop, one select call, and we react to whichever client actually has something to say. Reading a message from one client is only half the job. A chat server has to hand that message to everyone else in the room, and that's what actually makes it feel real time. So we write a broadcast function. It loops over our array of connected client sockets, skips the sender so people don't see their own message echoed back, and calls send on every remaining socket to push the message out. We plug that straight into the branch where we just read a message. The moment one client's data comes in, we immediately broadcast it out to the room, all within the same pass through the loop. Let's see it running for real. We start the server, then open two separate terminals and connect to it with a simple tool called netcat, which just sends whatever you type straight over a TCP connection. Type a message in the first terminal, and it instantly appears in the second one, and vice versa. That's real-time, bidirectional communication between two independent clients, handled entirely by our select loop and our broadcast function. Clients don't stay connected forever. People close the app, lose their network, or just walk away. If we don't handle that, our server accumulates dead sockets and eventually breaks. Here's the key detail. When a client closes their connection, our read call doesn't error out, it returns 0. That's the signal telling us the socket is finished and needs to be cleaned up. So we check for that 0 return, close that client's socket, and remove it from our array of tracked clients. That way our next select call stops watching a socket that doesn't exist anymore. One thing worth knowing, TCP is a stream of bytes, not a stream of messages. A single read call might return part of a message, or several messages stuck together. Real chat protocols add framing, like a length prefix or a delimiter, to know where one message ends and the next begins. This scales cleanly to 3, 4, or a dozen clients too, since our loop doesn't care how many sockets it's watching, up to whatever limit we set for the client array. Every connected client sees every other client's messages, in the order they arrive. Let's recap. We opened a listening socket, used select to watch it alongside every connected client, accepted new connections as they arrived, read and broadcast messages, and cleaned up anyone who disconnected. That's a real, working chat server. You might wonder why we don't just spawn a new thread for every client instead. You can, and plenty of servers do, but threads add real complexity, locks around shared data, and memory and scheduling overhead that adds up once you have thousands of connections. In production, Select has limits. It gets slow past a few thousand connections and its file descriptor set has a fixed size. Bigger systems reach for epoll on Linux or kqueue on macOS and BSD, which scale to far more clients. You'll also see thread pools, where a fixed set of worker threads handle client connections instead of one single loop, and TLS, which encrypts every message so nobody snooping on the network can read your chat. This project builds directly on core networking ideas, like byte order and how data gets packed for transmission over a socket. If you want to go deeper on those fundamentals, check out the Networking Basics lesson on the C Mastery Path site. This was an original project build, not pulled from one specific lesson script. For related C networking fundamentals, head to the link on screen and go build your own server.